for the invitation to this conference, and thank you all for being here. I have to apologize because there is nothing quantum in my talk. The only quantized things will be some charges, topological charges of some skyrmions and vortices. But I hope you will find it amusing issue. So essentially, I'm going to talk about Skyrmion lattices, some particular way that Skyrmion lattices show up in antiferromagnetic systems. In particular, we focus on the triangular lattice. And this is work I have done with Pierre Pujol in Toulouse and people of my group in La Plata, Rosales, Sturla, and Osorio. And well, there are things we are still doing I will mention at the end of the talk. So let me start with a bit of history about skyrmions in the literature. Then I will move to more recent issues about skyrmions having seen in experiments. And in particular, I will talk a little bit about ferromagnetic models and the relevance of Dzyaloshinskii-Moriya interactions, at least in most of the known cases, for the appearance of these skyrmions in the skyrmion lattices in the ferromagnets. And then I will shift to the topic of my talk, which is the antiferromagnetic triangular model with classical spins. And I will show you this new, well, state of matter is maybe too exaggerated. It shows up a new ground state in these systems that we dubbed antiferromagnetic Skyrmion lattice, but maybe one should better call it vortex lattice, or Z2 vortex lattice, as I will explain. I will show you the phase diagram in a field that we obtained by different techniques, numerics and analytics. And I will discuss also the low energy Hamiltonian and then some conclusions on the future work. Okay, so Skyrme was the first to talk about skyrmions, and this is what they are called like that. And so, but I'm more interested to what was found in the paper in 1975 by Belavin and Polyakov. Some people call them baby skyrmions because they are in one-dimensional space less. But I will say only skyrmions in the rest of the talk. But remember, we are talking about two-dimensional space nonlinear sigma models. And in this paper, they have shown that if you start from a ferromagnetic Heisenberg model, and you go to the continuum, then you get this nonlinear sigma model action. Okay, this looks like 3 Gaussian fields, but you have the nonlinear constraint that the norm of n has to be 1. So this is the definition of the nonlinear sigma model. And okay, here the order parameter is S2, so you have this topological charge associated to excitations. And so they have shown the existence of these metastable states characterized by this topological charge, which in terms of the spin fields has this expression here. So, okay, these were metastable states in the simple ferromagnetic model, but if you add interactions, these states could show up in some ground states. Yes, thank you. That's a mixture of notations. So it's just proportional. So the spin is simply S times n, and the constraint is that n squared is 1. Okay, it's just a number. Yeah. Well, the point is that usually one starts from the largest expansion, take the classical first, and then do an expansion on 1 over s. But here it has no meaning, because I'm going to concentrate only on the classical. Okay, so then essentially, if you add the Dzyaloshinskii-Moriya interactions, you will see that the models can condense these topological excitations in the in some ground states. Okay, so let me describe what are these two-dimensional skyrmions. So, okay, so essentially we have a model defined on R2, two-dimensional space, and the target space, because of this constraint, is S2. Okay. So sometimes it's for some discussion of these skyrmions, it's better to how do you say that? Sorry. No. To compactify, thank you. To compactify the space into S2. And so you have to care about these homotopy classes of the mappings from S2 to S2. And these are characterized by integer charges. In charge 1 skyrmion in a kind of shrink picture, it looks like this. So all the spins at infinity point in some direction. And, well, this is one possible configuration. And on the center, they point down. You can wrap this on the sphere, and it looks either like this or like that, depending on how you comb these spins in the middle. But essentially, you cannot go out from these skyrmionic configurations to a trivial one. Okay, so you cannot comb the complete sphere. Okay, so this picture is not very clear, but it's a way to imagine how you could get a skyrmion of charge 2. So that means that you have to wrap the sphere twice. Okay, so for charge 2 or higher, it's better to use this representation, but maybe if I have time, I will only discuss at the end. So just to get a better picture, because in 2 dimensions, sometimes it's difficult to imagine how to wrap a configuration on the sphere, there is a trivial analogy in 1 dimension less. If you compactify the real space into S1, and your target space is S1, then the similar situation happens. You have pi1 of S1, which is integers, and the different configurations, so you go around your space, which is an angular variable here, and then your field may turn once, or twice, or 3 times, or so on. And these configurations of the field, which are the black lines, are not deformable in a continuous way, one into the other. So typically, if you have a curve showing 2 points, these 2 curves are continuously deformable one into the other. But when you have these curves around the circle, then they belong to different homotopy classes. So this is the charge. This is a quantized charge of the, well, this will be 1-dimensional version of these skyrmions here. Okay, so this is for the one skyrmion. So what is a Skyrmion lattice, which is what has been observed in many systems. So it looks like this picture here. So you see red means spins pointing up, and dark blue pointing down. So on each of these islands here, you have one of these structures here. Okay, so it's like a tiling of this 2-dimensional space in a triangular arrangement of these charge 1 skyrmions, and this resembles very much the Abrikosov lattice. Okay, these are vortices because this is U1 theory, so they are the topological entities are vortices. Here, these are skyrmions because of the topology of the space and the fields. And so let me tell you why these structures are important or interesting. Yes, I will show you some experimental, and they are learning how to make them even more stable. So at the beginning they were just discovered, but then now they are cooking up some extra experimental ways to make them extend the regime of stability. So there are other cases where these Skyrmion lattices appear. So this is not a complete list. This is just one list I have found amusing. Yes. Yes, I think so. So this is was the first mention of these lattices appear in nuclear matter in 1985. Then more to the point that I am going to discuss today, there is an original paper, a very important paper by Bogdanov and Jablonski in 1989, where they studied 2-dimensional ferromagnet with some extra symmetry breaking terms, so in particular inversion symmetry breaking terms, like in particular Dzyaloshinskii-Moriya, and they were the first to show that in some Landau-Ginzburg description, these Skyrmion lattices could be the ground state of the system in some region. Okay, also in, these two related papers have to do with quantum Hall effect systems, where there was a big fuss in 93, 1995 about these Skyrmion crystals in quantum Hall effect systems. There are also mentions on this in a spinor Bose-Einstein condensates, so where we have this extra spin degree of freedom, and more recently in quasi two-dimensional liquid crystals, also these structures seem to appear. So they are almost appearing in many places, so that's why I say the ubiquitous. And I have checked that, so if you put in the archive Skyrmion on the title, there are 1,000 papers talking about that. I don't know if this is important or not, but at least it's a topic that some other people are looking at. Okay, so let me tell you, after this 1989 paper by Bogdanov and Dzyaloshinskii, where this was studied analytically, the big first or next step was done by Mühlbauer and collaborators studying MNSI. That, of course, is a three-dimensional material, but still they could show that in the magnetic field temperature phase diagram, there was some phase here that had this at the surface. Okay, this Skyrmion lattice structure showed up for the first time in experiments in this paper here, and they did a mean field analysis and they ended up. Okay, I will say more about this, but this is essentially M is S here. Sorry for the change of notation, but this is a nonlinear sigma model term, and this M dot curl of M has to do with Dzyaloshinskii-Moriya, but don't worry now. Let's go further. There are other nowadays. There are many others. So these were the first two, at least I have met in the literature. So these guys studied this material, and for different ratios of iron and copper and cobaltum, sorry, they have observed this kind of phase diagram. So this is again magnetic field versus temperature. So this is a almost two-dimensional system, and here they spotted this large Skyrmion lattice region. These are the images that where you can see. Okay, you cannot see well, but this has to do with a helical state. This is the Skyrmion lattice state, and this is when you arrive to saturation, the ferromagnetic state. Yes. Well, many lattice sizes, many. Yeah, depends on many things. But let me come back. I mean, I cannot be precise about the experiments, but I can show you in some models how this changes with magnetic field and Dzyaloshinskii-Moriya interaction. So in general, there are, I think, 10. Yeah, of course. There are extended objects in general. There are some particular materials where they could see what they call atomic skyrmions, that they have a few lattice size, but it depends also on the material. So you can have them very small or very large. So, and it depends on the ratio of couplings and the magnetic field, essentially. Okay. This dependence was already studied here, okay, because they studied a theoretical model, and they have established that depending on the couplings, the size of the skyrmions change. Okay, so this is a theoretical simulation of this system, which well, the model is essentially ferromagnetic coupling plus Dzyaloshinskii-Moriya and a magnetic field. Okay, in a nonlinear sigma model way, and it fits pretty nicely the experiments. Small angle neutron scattering shows very nice six-fold symmetry, which is related to this triangular structure of these skyrmions. And so this is just, I will come back to this in our models later. Okay, so let me go now to very sketchy theoretical explanation. Essentially, the best thing is to take your model and find what are the relevant ground state states, and then you will find the skimmer lattice. But there is a way to get a picture. So if you take Heisenberg exchange, so here I'm taking the minus sign here, so this is J positive means ferromagnetic. And in that case, okay, you get in the 1D simple case, you get just this state as a ground state. If it is antiferromagnetic, you get a kind of an L state. And if you are in some this frustrated lattice, like the triangular lattice I will discuss later, then you have this well-known so-called frustration, which means essentially that the system cannot simply satisfy maximally all bonds, but they have to organize in some way. So this is the famous so-called Mercedes-Benz structure for the spins in the triangular lattice. And so what happens if you add the Dzyaloshinskii-Moriya term? So let me say a few words about this, for me, unknown term until I started looking at these materials. So essentially, if you have two atoms with spins, and there is some exchange generated by the environment, and in particular, if you have inversion symmetry is broken, so usually this happens when spin-orbit coupling is important, then, well, okay, in this case, this Dzyaloshinskii-Moriya interaction will point perpendicular to the blackboard, and it will have this similar or proportional to this cross product. So essentially, in one case, one sign of D, the spins. So these are dictated by the structure of the material. Okay, so D to be cooked up from first principles or measurements adjusting experimental curves. But these are vectors that have to do with the symmetry of the crystal. And essentially, for a interaction like this in 1D, then you get a configuration like this, or rotating the other way around. So you see this is rotating clockwise. If you change the sign of D, it will rotate the other way. And if you combine these together with an exchange, so like a ferromagnetic or antiferromagnetic, then you start to get these kind of spiral states. Okay, if you put a field in the direction of same direction of Q of the spiral, then you will have kind of conical state. And if you add everything, so if you add exchange, Dzyaloshinskii-Moriya, and a magnetic field in two dimensions, then you get these kind of structures. Not everywhere, but in some part of the phase diagram. Okay, so coming to the materials, so people started sorry. Nagaosa and collaborators have done many important contributions to this subject, and in particular, they were the first to study, to try to fit MNSI experiments. And okay, this was a model proposed. This is just exchange in the cubic lattice. This is Dzyaloshinskii-Moriya. Here you see you have only one modulus, so all the Dzyaloshinskii-Moriya couplings have the same value, and they point here x, y, and z, so are the unit vectors along the three directions. So this is a typical expression of the Dzyaloshinskii-Moriya interaction in the, well, this is cubic, but also in the square lattice looks like that. And these terms are well, related to some need for stability. So the Ginzburg-Landau theory you get from this looks like, as I have shown you before, so this is a nonlinear sigma model term. Then you have this n dot curl of n, which comes from here, and then the magnetic field. And this worked pretty well to describe these experiments I have shown you before. Okay, an extra twist comes out if you add Dzyaloshinskii-Moriya to an antiferromagnetic exchange in the square lattice, for example. So in the square lattice, if you don't have Dzyaloshinskii-Moriya, yes, please. Previous? Classical. Yeah. Okay, so this is related to the ratio between K and J. So K is Dzyaloshinskii-Moriya and J. So it grows, so the period of this Skyrmion lattice goes linearly as J over D. I will come back to this in some analytica. Well, this was his question too. I think I have seen experiments where skyrmions in these lattices are very small, and they are called atomic skyrmions, so like a few lattice sites. But there are others that are tens of spins. Yeah, so they can be large. They can be large. I will show you what happens also when you put a magnetic field, because when you put a magnetic field, what happens is that the number of skyrmions may start to diminish, and then they become larger. Sorry, I have cough. Okay. Okay, so what happens if you had an antiferromagnetic exchange? So in that case, well, there are some experiments where they can take two ferromagnetic nanodisks, couple them antiferromagnetic, and create these entities. My thing is that if you have a Nel antiferromagnet and you put on top of it a skyrmion, it will look like this. Okay, so essentially it's the ferromagnetic skyrmion, but with an antiferromagnetic modulation on top of it. So the experiments they are doing now with this antiferromagnetically coupled nanodisk have to do with this picture here. From the experimental point of view, they can think of them as being two ferromagnetic skyrmions, and then spin current will move them straight instead of having some drift to the left or to the right. And this is now very on the fashion for those trying to do topological computation, because they can move this with currents, these guys, and they can spot whether they are there or not by looking at the Hall effect, so the anomalous Hall effect they produce. So they became very, well, at least they are studied by many people in connection with the possibility of quantum, sorry, not quantum, topological computation. I will say more later. Okay, there is another example that touches tangentially what we did. It was a paper by Okubo and collaborators in 2012, and they have shown that in a triangular lattice, they could get these Skyrmion lattices without Dzyaloshinskii-Moriya interactions. And here was the first indication that frustration may have an important effect on these Skyrmion lattices. And essentially what they took is a ferromagnetic first nearest neighbor triangular system with second or third frustrating coupling. So this is ferromagnetic, and this is one of the two is antiferro. For example, this picture here for this ratio. And in that case, well, this is a phase diagram, magnetic field versus temperature, and you have this here, this pink region here is the Skyrmion lattice. J1 is positive and J3 is negative, yes. So it's antiferromagnetic. Welcome. Okay, so then since I'm going to talk about... yes. No, but not so small, no? It's 1/3. The point here is that this is induces frustration, and this gives rise in a magnetic field. Without this Dzyaloshinskii-Moriya term, you get this Skyrmion lattice. Okay, so let me say some words about the antiferromagnetic triangular lattice. So one of the first papers that discussed the things I'm going to talk about was this Kawamura and Miyashita paper, where they have studied what happened with, well, this is a triangular lattice. So triangular lattice, you know, you have this 120 degree structure in the ground state, and so the order parameter is not like in the square lattice, as I mentioned before. It was S2, the symmetry of the order parameter. Here it will be SO3, okay? So some other group. And then you don't have skyrmions, but Z2 vortices, okay? These guys have studied numerically that in terms of temperature, so this here is temperature, and this is the number of vortices. They have observed that at zero temperature, sorry, at low temperatures, there are no vortices, and they start to appear in pairs when you increase. So these dots here are the vortices. When you go, at some point there is a transition, like a KT transition, but I don't want to enter into details. There are some similarities and some differences with KT. But essentially, you go from a phase with no vortices, and then they start to grow up, to appear. Okay, another paper, so this was this paper here, Kawamura and Miyashita in 1984. There was a later paper by Dombra and Reed where they looked at this triangular lattice antiferromagnet from a continuous field theory point of view, and they have okay, I forgot to put the sigma. So this is a nonlinear sigma model. I couldn't find sigma in my PowerPoint, so that's and then I forgot. So this is SO3 nonlinear sigma model, and essentially they discussed what is new in this description of this triangular antiferromagnetic case is that now, remember that in the previous case, in the antiferromagnetic, so ferromagnetic, let's say square lattice, we had S2, and I was talking about pi 2 of S2, which was Z, and here pi 2 of SO3 is trivial. So there are no topological objects associated with this group, but the first homotopy group is non-trivial and is Z2, okay? And this is why you have these Z2 vortices. But there will be no skyrmions if you look at this, okay? So now let me go to our work. So essentially, we studied antiferromagnetic nearest neighbor coupling. This is Dzyaloshinskii-Moriya interaction between first neighbors with delta R, which is the direction of the Dzyaloshinskii-Moriya vector that points along, where are they here? So this along like in the square lattice, okay, along the bonds of the lattice. So if you study this model with a magnetic field, no, delta R is just a meaning, no, it's fixed, yes. It's just, I don't know why delta is there. Well, it's this here, R prime minus R. So if you have fixed lattice, this is some, so it's the distance, it's the variation of R. This is why delta is there. No, it's fixed. It's just the distance between the two. And this is K is a strength that we will vary to analyze the different phases. So essentially, the new thing when you study this model here is that you get a state like this that I will describe in detail in the next slides. So, yes. No, of course, this is a toy model for describing some material, okay? So this is effective description. So essentially, what you need is some extra atoms around that break the symmetry and bring it this. Okay, that's a good point. Yeah. So if you apply the Moriya rules for the pure 2D triangular lattice, then you're right. But this is supposed to describe some real material. So you're welcome. Without this. This one, yes. So essentially, if you remove this is antiferromagnetic triangular with a magnetic field, and this was studied by, well, many people, and also Kawamura and Miyashita. And you have some plateau at 1/3 when you increase field, but very, very simple structures, so homogeneous structures somehow. No, let me go. Okay, so here you see that there are some entities, okay? So this was, we were happy for some time because we spent a lot of time looking for some things in antiferromagnetic lattices and we couldn't see any structure. And I think we were lucky to study this triangular case because of what I'm going to say later. This is a very particular of the triangular lattice, but there are other lattices where you don't see such nice pictures, but the same physics is behind. So, so what are these lumps here? So if you, this is triangular lattice, so you can see what happens per sublattice. So you have 3 sublattice structure, and if you look at each sublattice, what you get is a Skyrmion lattice. Okay, and this somehow is understandable because if you write this Hamiltonian, I've lost this red dot. If you write this Hamiltonian per sublattice, each of these terms will give you a kind of ferromagnetic or antiferromagnetic, but kind of square lattice type, and then you will have S2 as a parameter. So S2 will tell you that you may have this this topology, and this is what is observed. Okay, so just we were then we started to think about this in terms of this scheme. So you see that this is very interesting. So for your question, these simulations were done for d over j over 1/2, but we have done other cases. You need some value of d. Okay, there is some threshold. And the interesting thing is that you can also look at this and compute the vorticity. This is tricky because this is a lattice model. Vorticity here is related to SO3 degree of freedom, so you have to take 3 spins to define a matrix and rotate it around and make computations on all loops of the lattice, but this can be done numerically. And we are still working on that. And what you get is, so essentially this mess is this picture here, okay? And the dots are in the middle of any of these guys. Why there are so many dots? Because we have done different size loops, okay? The outcome of this is that there are regions where you get these dots close to the center of these lumps, okay? So essentially what's going on is that, so in any of these lumps, you have a vortex here, and so if you take curves like this, you always get vorticity, non-trivial vorticity. Okay, every time you surround the yes. Okay, so this is now this is a vortex number as a function of h. Yes, magnetic field, and here you see this is trivial. If you don't have a magnetic field, this will not be there. You will have just helical, okay, with some one wave vector. But if you increase the field, at some point, this number jumps and it behaves more or less constant. Okay, this has a lot of numerical error. This is ongoing, so you don't take this seriously. So with the magnetic field, you favor these structures. And then this vorticity goes down, and this is just numerical problems that we are solving now. Okay, so let me show you the complete phase diagram, at least for some value of d over j. As a function of temperature and magnetic field. So this was obtained with Monte Carlo simulations. And so you see this is spiral, but there are 3 sublattice spirals interpenetrated. This region here. Then you jump to this Skyrmion lattice region here, which is either you look at a whole lattice and you see this, which is a vortex lattice, Z2 vortex lattice, or the 3 sublattice structure, which are Skyrmion lattices. And then here, at that time, we didn't know what was going on in this intermediate region, but now we understood from here that, okay, there is some region where the number of vortices stay constant, but then the magnetic field starts to kill some of them, and this number starts to go down in a continuous way until here this should be 0. It's a problem of normalization in the computation. But so essentially, there is a phase here which is interesting, which I will describe a bit better here. So here is magnetization and susceptibility as a function of a field. So all 3 pictures are as a function of the field. So this is a previous one. This is a phase diagram. And here, let's see, magnetization just changes the slope, okay? But you see the peaks in the susceptibility because here, well, this is the chirality is a Skyrmion number, let's say, per sublattice. So if you look at this, you get 0. That's normal. It's a spiral. And then you get some number here, which is non-zero and almost constant, and then it starts to decrease. Of course, since this is a finite system, one has to check that this is a density, and density stays on 0. And this is we have done. And then it goes smoothly to 0 until it saturates. Okay. Okay, so this is specific heat as a function of temperature, where you see the peaks of the temperature. Of course, the peaks here, this is a clear first order transition. And here there is a continuous transition that we haven't yet analyzed. Okay. Okay, so let me say 2 words about finite size analysis. So you remember when you have this Skyrmion lattice, you expect something like this for the structure factor. And this is the structure factor for different sizes that you cannot see, but they go from 18 to 96. And if you analyze as a function of the size, the position of the peaks, they stabilize for large system sizes. Okay. So what we did more recently was to try to pop up what is the low energy effective action, and so essentially, okay, this I will go through this. This is standard computation. So you get spin fields, you do some gradient expansion, you compute the Hamiltonian, and what you get is this here, which looks nice because this is a nonlinear sigma model term. This is very similar to the Dzyaloshinskii-Moriya continuous version of the square lattice I have shown you before, and magnetic field. You have 3 Hamiltonians like this, 1 for each sublattice, and this guy, okay, there are some approximations. M here is S1 plus S2, or SA plus SB plus S3. So the 3 fields on the 3 sublattices. So it's a coupling term. I'm hiding some stuff here, but these are under control. I have made, this is not that you do this computation and you get this. So there is some numerical checks, and this is the, let's say, the very simple effective model that describes. Yes, here are 3 sublattices, A, B, and C. And this is the coupling term. And you see, this is very, very simple, okay? Of course, this is not what I wanted at the beginning, because I expect this to be described by an SO3 matrix field, okay? There should be a connection between the SO3 description and this. And this, well, we are looking at that. But my student is having very big problems to make the connection. But essentially, if you take this effective model and you analyze the phase diagram, essentially, well, forget about the details. So here you have S1, S2, and S3. And what you get is these ends, which are these ugly expressions here are simply the Skyrmion lattice for each sublattice. So essentially, you have for the A sublattice 1 Skyrmion lattice structure. For the B sublattice, the same but displaced. And for the third, displaced in another direction. And the 3 of them intertwined give rise to this expression. And this is essentially a comparison between numerics and this theoretical approach. Okay, we are trying to improve this. Fitting is not quantitatively correct, but qualitatively, yes. Okay. Yes, thank you. I'm more or less done. So this is another interesting thing. So let me come back. So you see here, I will now fix some magnetic field into this region, okay? So in order to have these lattices of Skyrmion lattices on each sublattice. And then I will turn off the magnetic field, the quenching, and see what happens with the different quantities. So as soon as you turn off, this is Monte Carlo steps. As soon as you turn off this magnetic field, the magnetization goes, this is blue, okay? Magnetization drops to 0 immediately. But this is a Skyrmion number, and this stays much longer. And this is because of topological stability. Okay, of course, this is a lattice model, and then there is no real topology. Otherwise, they will never decay. Okay, but here there are some energy barriers that can be circumvented, but still the stability is important. Okay, so this I will not talk about. So what we are doing now is to see what happens if you couple a quantum wire to this state. So via kind of Hund coupling. And let me mention some recent papers. So by Montome and collaborators, we have studied this. This is just fermions, hopping, and some classical spins. So this is a kind of spin fermion model in a magnetic field. And they see this red dot. This red here is the number of skyrmion, the skyrmion number, sorry. So they have charge 2 skyrmions, then charge 1 skyrmions, and then charge 0 skyrmions in this model here. This is a picture of charge 2 skyrmions. And why it's interesting is because I have met this lady, Ying Zhang, well, it's difficult to pronounce for me, but they have been looking at these materials, and they have observed in this is this centrosymmetric biskyrmion magnet, which has some structure, and they see in some region of H versus T this biskyrmion lattice. So that's something we are analyzing now, how to get how one can reproduce this lattice, skyrmion lattice, but now skyrmions have charge 2. So let me conclude. I think, yeah, okay. So what I have shown you is that in these antiferromagnetic systems, there is this structure of three skyrmion lattices interpenetrated that produce this Z2 vortex lattice. So this pops up the question of whether one could relate the two quantized topological objects, right? So it's a kind of combination, or I don't know, a bound state of skyrmions that lead to a vortex, Z2 vortex. And the other issue is that now we are looking at the Kagome lattice with the similar ideas, and these nice pictures I have shown you are not compute the vortex number. Then you have the behavior zero vortex number, then jump, and then some of the region of a non-zero vortex, Z2 vortex lattice would be there. Okay, some stability of this topological charge states has been discussed, looking at these quenches. Now we are also looking at this stability under deformations of these skyrmions. And so sometimes you can have skyrmions with some shape, depending on the interactions. And okay, there is this, people are talking about this data, or like of topological qubit, in the sense that you have a skyrmion or you don't have it. And spin and electron transport is also much on the fashion. There was a paper by Bhaskaran on skyrmion superconductivity. That means what happens if you put electrons on top of these backgrounds? Well, all these, I think skyrmionics now is a term that you can find in different places. So let me end up with some advertisement. So we are organizing a school and workshop in next year here. It's called Latin American Workshop, but people from other countries are very welcome. And so the title is Novel Phases in Strongly Correlated Systems. I am organizing this with Daniel Barsi and Daniel Sariolo from Rio and Pierre Pouchol from Toulouse. And I think that's all. Thank you very much for your attention.